Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini-episodes on topics in data science, machine learning, statistics, and artificial intelligence.
All right, Linda, before I announce the topic for today, because I want to give you a minute to think about this, what is the most complex task you've ever undertaken? This is related to our topic for today, EXP-Time, or Exponential Time, that class of algorithms.
What is the most complex task? I don't know. What makes something complex? A lot of steps?
Exactly. Good job. You've been listening to these last couple episodes. Yeah, I don't know. What about planning our wedding? That was a lot of steps.
Yeah, I was thinking that. I was like, that's a lot of steps. But actually, the steps weren't that bad. It was the fact that I didn't know anything. That's what made it bad. Doing everything I had to learn.
All right, so at the wedding, what if we had doubled the guest count? Would it have taken you double the time?
No.
Yeah. So actually, you might say that wedding planning is very efficient, or the algorithm that you execute to do it, because even as the input size grows, the runtime does not grow. It's actually sublinear.
Yeah, after a certain number, it's still the same amount of work. We just tell the caterer or the floor person, there's 300 instead of 100, but I don't have to give you any additional direction.
Exactly, yeah. There's no new problem to solve.
Yeah.
Although maybe at some scale, like, there's a new venue and blah, blah, blah. But we've also kind of mentioned linear algorithms, which are technically polynomial time. It's a polynomial to the degree of 1 is linear. And then, of course, we've talked before on previous episodes how we'd like our algorithms to be efficient. And broadly speaking, that means they could actually run on a practical problem, aka they are considered in class P. They run in polynomial time in the size of the input. What if we had a problem that was, instead of polynomial, exponential, like it took 2 to the n steps, or 2 to the n squared steps, or something like that? Can you see asymptotically how that would be more difficult than a polynomial time?
What do you mean by asymptotically?
As n grows, how do those two functions grow?
So then what's your question?
Which is worse, polynomial or exponential?
Oh, exponential.
How do you know?
Well, I don't know, but I'm guessing. You asked me a question, so I answered.
Well, you got the right answer, but I want you to show your work. Maybe we should give some examples, some practical examples of EXP-Time algorithms. One is Generalized Chess. If you want to win at the game of chess, you have to solve an exponential time algorithm, or at least as far as anybody knows. You ever played chess?
Yep. Was part of the chess club in middle school.
Oh, yeah?
I told you that.
I know, but the listeners might be listening for the first time.
Oh, okay.
Why did you quit?
Well, they didn't have a chess club in high school.
Oh, that's disappointing. Did you have a ELO rating?
No, we didn't. We weren't really that competitive.
Did you have any particular strategies or openings that you learned to do?
No, we weren't really that focused on technique. We were just focused on learning chess and playing it.
I gotcha. Yeah, that makes sense. So you'll notice I said generalized chess. Let me explain what I mean by that. You're used to chess is 9 by 9, I think. That's the grid. And in theory, you could have a bigger board with more pawns and more pieces, or even just the same pieces, but the board is, 100 by 100, and you got to play it in a large room, and it takes a while to get across to the other side of the table to attack or whatever. That is a harder computational game because there are more possibilities. The basic game of chess has a huge number of possibilities, but if you made the board bigger, you just make more and more possible game configurations.
Sure. You have more players and you have more slots and options to put the players. So that means you have more moves.
That's right. So in complexity theory, we usually like to talk about what's called a decision problem, which basically means you can answer with yes or no. So generalized chess, we would say the problem is you ask a question like, can white force a win?
What do you mean by forcing a win?
Well, forcing a win would mean that as long as you don't make a mistake, you certainly are going to win the game. Even if your opponent has the best possible defenses, they're just at such a disadvantage that at this point they're going to lose unless you make a mistake. So forcing a win means you have at least one path of moves that regardless of what your opponent does, you can win.
So it means you are destined to win, not your opponent? Can one of the players force, and I'm assuming they want to force themselves to win?
Sure. That is a decision problem in exponential time. Do you have any idea what it would take to answer a question like that?
Well, you have to know the moves, and then you have to estimate what the moves are after it.
Well, what if you don't want to estimate? What if you want to know for sure? And what if, when you say you need to know the moves, what if you wanted to calculate them? If you know the rules of chess and you see the board, you can calculate all the possible moves a player could take. Might be tedious, but it can be done.
Sure, you could hypothesize what all the moves are.
Okay, so let's say we're going to check, can white force a win? In chess, I've heard the branching factor is about 19 on average. Don't quote me on that, but basically that at any typical moment, a player has about 19 possible things they can do. Let's now talk about how that algorithm would be implemented. So its input is the current board configuration, where all the pieces are, and whose turn it is. And like I said, there's maybe 19 different moves you could take. So it doesn't know which is the best one, but it kind of needs to check them all and say, can any of these available moves force a win? And you don't need multiple moves to force a win, right? You only need one move. As long as there's one and you pick it, you can force the win.
Well, you need to have all the moves leading up to it to force a win.
That's right. So now let's think about the trace that this algorithm is going to have to do through all of the possible future plays, right?
What's a trace?
A trace is like to go and check things out. So it's sort of like saying, well, what if I did this and you did that and then I did this and then you did that? And then we just sort of analyze the back and forth of what moves might be taken. But of course, we don't know the opponent's moves, do we?
Well, for me to estimate my moves, I actually need to estimate what the opponent will do.
Yeah, you definitely want to estimate as a player. But if this computer is going to be reliable, if it's going to be perfect in deciding if someone can force a move, then it either has to check them all or maybe be very clever in knowing how it can like prune some of that search tree and not look down certain paths. Like if a move is really stupid, maybe recognize it and not consider it. But in general, it's got to check all of your available moves, and then it's got to check all of the opponent's possible responses to that move, and then it's got to check all of your responses to the response to your move, and then it's got to check all of the responses to the response to the response of your moves, and so on and so forth. So can you picture that as like a tree? Each possible move is a branch. How quickly does that tree grow out into a giant bush?
I would assume pretty rapidly.
All right, Data Skeptic listeners, I'm going to list 5 companies right now. You tell me what they have in common. NPR, Fender, New Relic, ZipRecruiter, and Adobe. 5 companies that were not founded in my kitchen. But they are 5 companies of which I've been a customer, and all 5 of them, and some 900 more, gave Periscope Data a try, and today use it as part of their process for making data-driven business decisions. By the way, if you're going to AWS reInvent November 27th through 30th, Periscope Data is going to be there. Stop by their booth and say you heard about them on Data Skeptic. So what can Periscope Data do for you? The most efficient way I know how to make the pitch? 5 things. Ingest, store, analyze, visualize, and report. Periscope Data makes each of those steps easy. Explore your data much more efficiently, create all sorts of automated reports and alerts, all this in an easy-to-use interface that anyone who knows SQL can work with. See if Periscope Data can be an important part of your BI toolbox, just like it is to tons of other companies. Get a trial going at periscopedata.com/skeptics.
I would assume pretty rapidly.
Yeah, because at every level, you're considering another 19 possible moves. So it's like as you search through all the possible games, that's essentially what you have to do is like search through all the possible remaining games to find if there's a path that leads to a win. And this would take, as far as anyone knows, this would take exponential time.
Okay.
Another interesting exponential time algorithm is asking, will this particular machine, you give it some other computer or some other program and say, will this halt in K steps? Will it finish its work in, basically, will this algorithm always be done in 10 minutes? Something like that. A question like that is in exponential time.
What do you mean the question is in exponential time?
If there were ever a program that could answer that question correctly and never make a mistake, then it would require an exponential amount of time to come up with the answer. In other words, there's no efficient way to answer that question.
So then how do you solve them?
Well, mostly you can't even brute force an exponential problem like we did with NP problems where you could check all of the possible solutions and then just verify them efficiently. Exponential time can't even be verified efficiently. Let's think of what it would look like if it could. If someone came to you and said, aha, you're playing chess right now, I can tell you the exact way to win the game. Here's what you do. You move this piece and then next turn you move this piece here. and all that kind of stuff. Whatever they tell you, they're not going to say like, well, the opponent is definitely going to do this, right? You're going to do this, they're going to do that, then you're going to do this. You don't know what their moves are going to be. So you can't even verify a strategy like that. The strategy has to include the responses of the opponent. So you would need more than polynomial time to verify whatever that provable strategy looks like. You can, I'm not even sure if you can give someone the equivalent of a witness string.
What's a witness string?
Witness string is just like the solution, basically. It says like, here's the way to win the game, a description of the winning strategy.
So you can't give someone the solution unless you process all of the options.
Well, either I think, that solution, that strategy, either it would take up a lot of space to describe it. The description would be really, really long compared to the input. Or maybe it's not possible to even give someone a solution like that that they can verify. I'm not sure. One of those two. But either way, I know you can't verify in polynomial time that someone's given you a good solution.
You can't verify.
Yeah.
But you can process all the options.
That's one property that sometimes makes problems in exponential time. A lot of like games or adversarial situations or sometimes simulations or like computing the best decision in a complex problem. These are the types of things that end up in exponential time. That's a good example, like picking the best decision. Like if you want to, get a new job. There's a lot of things that go into that, right? Like your salary. You could have a strategy of saying, well, I'm going to pick the company that offers me the best salary, and that's easy. But what if you're also concerned with what you're going to learn at that job or what opportunities will be opened in the future of your career? Well, then you have to consider like, okay, well, what's my career look like if I first take this job, then I take some hypothetical other job later? Could I have gotten that same job if I went to the other company? And there's all these sort of like, what if this, what if that situations that make this a complex decision problem.
Is that why people are stressed?
Yeah, maybe that's a fundamental biological process we've just discovered here, that our brains release stress chemicals when they encounter exponential time problems.
So next time I encounter a problem, I'm going to say it's an exponential time problem.
Well, you will need to present the algorithm that shows it's in exponential time. And then if you really want to convince me, you have to make it exponential complete. Prove to me that no algorithm could solve it faster than exponential time. But yes, that would be a thing you could do that would be really interesting. So I bring up exponential time as our topic today because it's yet another interesting complexity class, in our little running theme we have going on here. There are so many complexity classes. In fact, you can go to a site called the Complexity Zoo that was founded by a future guest we're going to have on the show. And it lists, I actually like to go read these once in a while just to see if I know all of them. Some of them are a little bit obscure. But EXP-Time is one that you can kind of encounter in your everyday life. If you want to get into this stuff, you should know about P, NP, that we talked about both of. Then you should know about P-space that we're probably not going to get to on the show, and EXP-Time that we talked about today. Those are your central core ones. Oh, and maybe as a data scientist, learn about NC next class. Other than that, just, dabble in what's interesting to you. But I'm glad we got to talk about exponential time as yet another example of complexity classes. And it's one I think is very relevant for AI because an artificially intelligent machine is going to have to make smart decisions, and smart decisions require planning, and a lot of real-world planning problems are in EXP-Time. Lastly, you wanted to have a membership drive, huh?
Me?
Yeah.
Yeah. We're going to designate 2 times a year where we're going to ask for your support.
And we're going to have an annoying telethon thing that's like 3 hours long with no content.
No, we're
going to
get
a duffel bag or whatever.
We're going to have a very cute and short ad either at the beginning or the end of the show, just asking for your support for all those listeners out there. And we only ask, now we decided we're only going to ask twice a year.
All right. I like that. So how are we asking? What's the call to action here?
Call to action is go to our website and make a one-time donation. Our target donation is $40, but if you don't have
steep.
40, try 20 or 10. But this is a one-time donation. Also, it's time for the holidays, so you could also gift it. You can also say you donated to, we're kind of like a charity, but we're not.
We are not a charity. You cannot write this up.
We're not a write-off, but we do things for you. We provide a service, and we hope that because you're listening that you like this service and that you'll donate.
All right, yeah, and if you can't, just spread the word. Tell your friends about Data Skeptic. I also want to get a message out there. Linda's been hyping the one-time donations. Give to the show in whatever way you feel comfortable. We are fortunate that we have many consistent subscribers on a monthly plan. I can't thank you guys enough. And I want to let you know, anyone who's on a monthly plan, be looking out for an email from me in the next 1 to 2 weeks. And if you want to get in on this, go sign up real quick, because I'm going to send all the members an email where I'm going to confirm your mailing address if we have it. Some we do, some we don't. If you do not hear from me by like December 15th, definitely shoot me an email if you're a member, because I want to get that cleared up. I'm asking for your mailing address. I mean, you don't have to give it to me if you don't want to, but we want to send something special to all the members, so make sure you get on our radar for that, and then be looking for something to come via the postal service soon. And yeah, like I said, if you want to get in on that, sign up as a monthly member, ASAP, dataskeptic.com, click on membership or members or something like that to do it. Well, thanks as always for joining me, Lindy.
Thank you, Kyle.
As always, I want to remind everyone to keep thinking skeptically of and with data. Good night, Linda.
Good night, Kyle. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.